Good afternoon, everyone. I am Idriss, PhD candidate at University of Padua. I'm going to present our work on Tchaheu monitoring of bridge, integrating OpenBIM, GIS and IoT in the Breganze Bridge case study. Our presentation is structured as follows. Bridges are critical infrastructure. It sometimes happens that they collapse, causing death and economical loss. Therefore, structural health monitoring is used to track and measure the response of the structure in several fields. Any anomaly affecting the structural performance can be detected. The structural health monitoring system uses sensors placed at different locations of the structure, and the overall workflow is analog to the human brain system. While integrating structural health monitoring with bridge information modeling, we found that it often lack the metadata validation within the BIM model and also the sensors inside the BIM model. Additionally, the sensor and the host element are usually close in the model, but are disconnected entities within the model. And finally, when we look at the previous work addressing the model update, they use either proprietary data format or OpenBIM workflow using dual database integration. Our goal is to use Information Delivery Specification to validate the model to ensure that all the metadata are present. Additionally, nexting the host element with the sensors and implement the simplified IFC model update procedure with the sensors within the database. And finally, try to visually identify the host element which the sensors value are below or exceeding a specific threshold. The methodology adopted is as follows. We start with the definition of human and machine head-based specification. Then the human head-based specification is used to do the creation of the digital model, and we export to the IFC. Then we validate the model using BIM with the machine head-based specification. Then we pass to the definition of the database and injection of those data. Then, moving to the fourth step, we next the sensor with the host using IfcElementAssembly, and we retrieve the data within the database and update the different sensors. Finally, we develop a web-based platform which enables us to visualize the model within the open source library MapLib and using IfcGIS also. Here we have the human and machine head-based specification defined at the beginning using IDS for a specific accelerometer, and here it's the overall model present in IFC with the sensors and the different properties. At this point, we can see that after the validation, our model complies with the defined information requirement that we perform at the beginning. Moving to the grouping of the sensors with the host element, we can clearly see at the beginning that the BIM element and the sensor was separate in the model. And then the idea that we got is to insert in the host element the sensor's name. For each host, we have the sensor's name. Then we use Python script with IFC OpenShell library to pass the IFC model and match the different entities and group and aggregate the sensors and the host element and the different sensors. At the bottom right, we can see now, for example, a BIM element with 4 sensors hosted together. Regarding the model update, we also query first the database, then we extract the name within the database, and we use again a Python script to match those names with the one in the IFC, and finally update the model with the significant value such as the max, mean. And we can see on the right side the initial state where the model is not yet updated, and the final state where the model is updated with the displacement value. Here we have a small demo of what we perform. We are able to visualize the bridge model in GIS environment to understand the spatial context. Also, when we double-click on a specific sensor, the measurements are automatically displayed. Similarly, if we double-click on a specific bridge element hosting a sensor, the measurement is also displayed. We can also have the whole list of the different IfcElementAssembly hosting the sensors, and selecting one of these elements automatically display the measurement of the different sensors. Finally, we have a threshold measurement system where we can identify the measurement, the element hosting sensor value below or above a specific threshold. Those are in green are those below the threshold, and those are in red are those above the threshold. To conclude, we were able to develop a visual interface where we can access the bridge model, the sensor data, and the capability to have an awareness of the spatial context. We also validate the presence of all the metadata and managed to link the sensors with the respective host element using IfcElementAssembly. However, due to the metadata dependency, we plan to address this limitation using spatial collision detection based on the 3D location of the sensor and the host. We also were able to evaluate the localized element behavior, such as the displacement, the tilt angle, and we identify elements which are exceeding or below a predefined limit. As further study, we also plan to integrate operational model analysis with numerical data coming from the FEM model to explore also the global structural behavior. Thank you for your attention.